Sometimes when we're trying to solve a higher order differential equation, we'll find some solutions, but others will be missing. In the situation where I'm trying to solve a second order differential equation, and I find one solution, but not the other, then a reduction of order can help me. If I can reduce the order of my differential equation from second order to first order, then all of the techniques that we have for solving first order differential equations become relevant, and I can use them to find that second solution. To do this, I need to use what's called a reduction of order. So in order to do a reduction of order, we need to know one non-trivial solution to a linear second order differential equation. Then we can use that to find a second solution by reducing the linear second order differential equation to a linear first order differential equation through a substitution. Now, that substitution relies on the fact that if we take y2 divided by y1, it's not constant. So we saw that before, the idea that if we have two linearly independent solutions, that ratio can't be a constant. We didn't do it directly, but it was a consequence of something that we talked about. So that means that that ratio must in fact be a function of x. So if I take y2 of x divided by y1 of x, where y2 and y1 are my two solutions, it's going to equal u of x. Since I know what y1 is, I can solve for y2 of x by simply multiplying by y1, and I'll get y2 of x equals u of x times y1 of x. Now, that's the substitution that I'll be making into my differential equation as the solution in order to reduce the order of my differential equation and to give me the chance to find my second solution. Really, the best way to understand this is to go through an example and see how this plays out. So let's do an example. So we'll be given a differential equation. We have a second order differential equation of y double prime minus y equals 0. We're given a solution, e to the x. You probably could have found that solution even if you weren't given it, given what you know about the derivative of e to the x. But we're given it, so we don't have to go about finding it or worry about it. And we're given an interval of negative infinity to infinity. So to reduce the order, the first thing I do is make a substitution into my differential equation. My substitution, as we saw. So the first thing that I need to do, since I have a second order differential equation and I have one non-trivial solution, is I need to make a substitution. Namely, y equals u of x times y sub 1 of x. Now, y1 of x I know is e to the x, so this is really u of x e to the x. So everywhere I have y, I'm going to substitute in y equals u of x e to the x. So I could do that. So I'll get y double prime minus u of x e to the x equals 0. Now there's still a y in there in the form of the second derivative of y. So I need to find the second derivative of my substitution in order to make the full substitution. So the first derivative, I have a product of functions of x here. So my first derivative is going to be u prime of x e to the x plus u of x e to the x, using the product rule. Now I have to find my second derivative. So y double prime is going to equal, and again, now I have products here, so I'll have u double prime of x e to the x plus u prime of x times e to the x plus, and it's another product, so plus a u prime of x e to the x plus u of x e to the x. So I've used the product rule in both parts of my sum. So now I can simplify this by combining like terms, so I'll get y double prime equals u double prime of x e to the x plus 2 u prime of x e to the x plus u of x e to the x. So now I can substitute that in for y double prime. So I'll have u double prime of x e to the x plus 2u prime of x e to the x plus u of x e to the x, and then we still have minus u of x e to the x equals 0. Combining like terms, I have plus u to the x e to the x minus u of x e to the x, so those zero out. So I end up with u double prime of x e to the x plus 2u prime of x e to the x equals 0. Now you might be thinking this doesn't look terribly simple yet, but we have a little bit more to work with here than we did before. So I can now factor out an e to the x. So I get e to the x times the quantity u double prime of x plus 2u prime of x equals 0. And now I know e to the x does not equal 0, ever. So that means that u double prime of x plus 2u prime of x must equal 0. Since I have a product that equals 0, then one part of it has to equal 0, and that must be the u double prime plus 2u prime. Now what I've done is I've made it so this is the differential equation I need to solve. Notice I don't have any u's in here. I only have u primes. So we're going to let w equal u prime and basically take this down a derivative in doing so. So that means that w prime will equal u double prime. So I'm going to make that substitution. So I end up with w prime of x plus 2w of x equals 0. And now this is a first order differential equation. It's a linear first order differential equation. So I can use an integrating factor to solve it. And if I work with that, my integrating factor is going to be e to the 2x. So what I really have here is the derivative with respect to x of e to the 2x w equals 0. So when I integrate, I'm going to end up with w equals c1 e to the negative 2x. And now I can change my w back to u prime. So this is going to tell me u prime equals c1 e to the negative 2x. So now I can integrate again to find that u equals negative 1/2 c1 e to the negative 2x plus c2. And now I remember that y equals u times e to the x. So I can now multiply u by e to the x to get y equals negative 1/2 c1 e to the negative x plus c2 e to the x. And now, since I want a solution that is linearly independent from the first solution, and the first solution was e to the x, then I don't want to include this second term. So I'm going to let C2 equal 0. And I want my first term to be as simple as possible to work with, though any multiple of it will work. So I also get to choose a C1 value to be part of this general set of solutions. So C1, since it's being multiplied by -1/2, might be really nice to choose it as -2. So when I plug in C1 and C2, I get -1/2 times -2 e to the negative x plus 0 e to the x, which will equal 1 e to the negative x plus 0. So I get a second solution of e to the negative x. Now I could go through and I could check and make sure that I've made the right choices to get my linearly independent solution from the first one by checking the Wronskian with both. And that would confirm that I have my desired two linearly independent solutions to the second order differential equation.